Dear audience, welcome to our initial session on 3D machine vision. In this presentation, I shall introduce you to the technologies and application areas where 3D sensing is important. But the main goal here is that you get an overview of what the concurrent developments are and that you can find your way when you consider implementing a 3D machine vision solution yourself. To set a stage, I will look at the motivation for 3D machine vision, and I will show you some historical projects in the 3D field. This shall then lead us looking at particularly useful 3D sensor technologies and how they are applied concurrently. And finally, I will focus on 3D cameras that can be used for various setups and applications. So why should we care for 3D sensing at all? The basic answer to this is that our world comprises of 3 spatial dimensions, and thus 3D sensing, and only 3D sensing, gives a more complete account of our world. And historically, looking at 3D positions, we can look at mechanical tactile sensing, in particular for quality inspection. So this is one of the precursors of 3D machine vision. In this case, one of the motivations for 3D sensing is to improve upon such mechanical coordinate measuring machines. However, not necessarily with the same accuracy for a while. In this animation, you can see how such a machine is able to trace a 3D shape. Besides inspecting 3D shapes, there are also a number of tasks where 3D positions are required. And here we already look at vision-based robot guidance. This shows an early robotic system, including 3D sensing, that was developed in the 1980s for a specific task of automated arc welding. And in this case, a laser line triangulation was constructing. And this working principle is shown here on the left-hand side. A laser line is projected onto the object surface, and a detector observes that line from a calibrated angle. And this allows to receive the object edge position because the detector sees a displacement in the laser line at the position of the edge. And in this slide, we already see 2 major ideas in 3D vision. One is the large field of robots performing a task that requires a great flexibility. And for this, to achieve this, one can use 3D vision to guide the robot along. In this case, the shape for welding is not predefined in detail or might change from part to part. And the second good idea here is the 3D technology of sheet of light or laser line triangulation that provides us 3D distance data when we have scanning. And in this case, the robot arm itself provides the scanning movement along the part. Let me move on to another interesting project in the 1990s. In this case, the task has been to use 3D vision to create an accurate digital 3D model from a shape. In this case, it was a unique classic car shape. No digital drawing data was available. And here in this work, the full 3D shape of this classic car was actually constructed. First, they put markers on the shape. You can see those markers on the right-hand side in the image from the lab. And then the detailed shape around those markers that are reference points were derived using the structured light approach. Here, you can see on the lower right-hand side that the whole shape was covered patch by patch along the car. And so structured light is a technology that gives us a patch of the surface at once, instead of only a single position as for the laser triangulation we just looked at. Now let's look at the software side. 2D data can be stored and handled in pixel arrays of gray values or RGB values. So this can be stored. This format can also be stored can also be used to store one value, namely for example, a distance value, and then we call this a height map. A height map has a unique advantage for processing because all the 2D algorithms that are there, like edge tracing and so on, can be used on a Z map as well. However, this is not truly 3D data because usually what you also want is X and Y in millimeters. So we needed to introduce more complex data formats, in this case point clouds, to store X, Y, and Z in millimeters. Point clouds are now the general representation of 3D data, basic representation. However, as compared to 2D images, there is no neighborhood defined in point clouds. So if you look at this depiction on the slide here, you can see a 2D image and then the corresponding height map on the right-hand side. But if you want to store also the X and Y positions of each of the surface patches, you need to go to a point cloud to store this. In the 2000s, these data representations were introduced in the major machine vision libraries. And then along with them, they needed to propose some processing features. First of all, calibration, and I've marked this with an exclamation mark here because all the 3D setups that we look at require calibration functionality. And then you want to have more complex tasks in the software on the algorithms, like you want to combine and align different 3D data sets, like we've looked at the patches of the car just before. You want to create a surface from points that is meshing. And finally, one of the most complex algorithms are used for model fitting. That means you take a point cloud and you want to detect and locate objects using for example, their drawing model in this data. So for this presentation, this look at the software and algorithm side shall be enough, because now I want to cover the major technologies that are there currently. We've already introduced laser triangulation, but this will not be the only one. So the question that stands over this summary here is whether not each application requires their own technology. And I will try to show to you that while this may have been the case for the niches, now we are into the area where actually a few key technologies can cover many applications. So let's look at those. I've already introduced laser triangulation. Now this setup of a laser sheet that is projected on an object and a detector at an angle has been integrated into one housing in the 2000s and also has become smart. And smart here means that here no longer this so-called sensor then gives out the displacement only, but it already gives you a result whether the shape that you expect is there or not. So in this case, using a laser for projection can provide contrast on many different surface areas. So this kind of sensing technology can be used on many different objects. However, scanning an object, that means getting more than a single position or single line coverage, you need to control the movement. We have seen previously that a robot could control the movement. Typically also objects can have movements that are controlled, like conveyor belts or rotating tires, for example. So these applications lend themselves well to laser triangulation. However, if you want to cover very large areas, you need to go quite distant to allow your laser to basically fill the whole field. And that means you have to put in a lot of power, and that will usually end up in a laser class beyond laser class 1. And this means there are eye safety concerns, and you need to have some protection in these large-scale applications based on this technology. Now, we've also already mentioned structured light approach. So here, this technology is a bit more complex than the laser line triangulation, but essentially you only go from projecting one laser line onto the object to project, for example, many lines at once. And then you also triangulate to find out what the distance for each of these, along each of these lines are. However, this will only still give you a limited or sparse coverage only when you use several lines. So what you typically do in this setup is you sequentially take on several patterns, and you decrease the spatial frequency or increase the spatial frequency of the, in this case, in this visualized case here, the stripe patterns. You can see in the image here on the lower side, one of these patterns projected on a car seat. And this one pattern is not enough, but several patterns used sequentially can then create on the right-hand side a point cloud or 3D data, 3D image of the surface of this seat. To get these kind of patterns onto the object, there are different projection technologies that can be used. However, of course, as you can imagine, they have to be more complex than the laser line projection. And in addition to this sequentially applied pattern, you can also shift patterns and use so-called phase shift to be even more accurate with this technology by taking time to move the pattern over the object during the acquisition. Now I would like to come to a variant of structured light. So as I just mentioned, structured light was generally using several patterns, and that means it lends itself to static scenes. However, if you want to apply that for dynamic scenes, there is also a nice variant. You can use a single pattern and then use only one acquired image to do a triangulation, but then you have to cover the different spatial, you have to provide the spatial resolution that you want in the projected pattern already. And notably, Microsoft introduced such a device in the consumer market in 2010. That was the Kinect first generation. And you can see here on the lower right-hand side, the 2D pattern that was projected by the Kinect. And for each of these points in the pattern, then a triangulation can be done if the point can be identified correctly from its surroundings. So this is a variant of a structured light approach that can be used for dynamic scenes because only one image acquisition is enough to cover the area with depth information. And you can see on the lower left here an image taken by the Kinect. And it lends itself to situations like where you observe people and observe motion or gestures in the room. And as you may know, this was the principle for the Kinect. It was to help gamers by steering their computer game via gestures, for example. The next technology I would like to show you is stereo vision. There are passive and active variants of these. I mean, when you think of stereo, you must think of mammal vision. So stereo follows the paradigm of human-like vision. So nature's evolution has actually fixed that two eyes are really a good system for mammals to have 3D perception. And stereo, of course, builds on that. What does stereo do? You can see in the upper right-hand side that you take two images, so use two cameras, look at the same scene, and you will get two images that have a slightly different perspective. And now the task in stereo vision is to find the corresponding pixels or find the corresponding objects in the images. You can see on the lower right-hand side, if you start with the left stereo image and you look at the top of this structure, you have to find this same piece in the right-hand image. And once you have done that, you can basically mathematically triangulate and find the distance of this structure in the scene. As you can imagine, this process of comparing these images is computationally expensive. So this technology became popular when sufficiently capable computing and sufficiently capable algorithms were developed to provide fast stereo matching. In the case that is shown here, we look at colored stereo images, and you can imagine that finding correspondences in these kind of colored images, which show a lot of nice structure, that means a lot of texture, is possible. However, if we look at industrial setups, we often come to situations that have not such natural texture. So here in the upper image, you can see that foreground and background of this cup are actually very homogeneous, and in consequence, here we see that only part of this scene, only part of the cup is colored. Colored here means that we actually have a distance measure to this part of the cup. So there's a lot of distance measures missing here. And why is that? Because of the homogeneity. It's for the algorithm not possible to find matches, find exact matches if the incoming images are too homogeneous. So no unique matches can be found. In this case, in our Ensenso cameras, we help that by introducing artificial texture using a projector. This is a development that led to compact LED-based projection modules. And you can see on the lower side here how big the benefit here is, that putting the texture from a projector into the scene and making this texture such that it's almost unique for every pixel allows us to get a filled representation of the scene, including foreground and background and the cup itself. So that's almost complete using this active stereo technology. Finally, there is one more basic technology used today, and that's time of flight. So what is time of flight? The name says itself that we want to measure the time it takes light to get to an object and be reflected back. So we need to sense time, or we need to sense light travel time. So as you can imagine, as light is very fast, this is not an easy task, and it cannot be done by a regular 2D image sensor. Since long, the approach of sensing the arrival time of light has been realized in so-called LiDAR systems. That's parallel to the radar systems. And LiDAR you can typically see in devices that you can use in your household to get single point distances to a wall and so on. So you would basically arrange your kitchen using such LiDAR points. However, also in industrial setups, LiDAR is popular. As I said, you can do 1D ranging, so get only one distance point at a time. But soon enough, scanning LiDAR systems were introduced. And how do they work? Well, you can see in the animation that basically if you insert a rotating mirror and send this laser line or this laser point around in a curve, you can easily basically cover a 2D plane and get distance in that plane. And furthermore, now if you use several of these laser dots in parallel at different heights, you will get a 3D coverage, so you can basically get your surroundings. So that's a 3D ranging with scanning LiDAR systems. One particular advantage of using time-of-flight technology is that the time difference that you get from an object which is a certain size or a certain size difference does not depend on distance to the object. So while all triangulation methods we've discussed before have a stark dependency on the distance of the object, time of flight does not in principle. So looking at scanning time of flight is one thing. Of course, it was always interesting to look at imaging using time of flight. This became possible also in the 2010s. And here I show another Kinect, the Kinect second generation, because this is one of the first devices including a large sensor that is using time of flight as measurement technique. In this case, in this imaging sensors, you would either resolve the pulses that are sent out, or you basically use a continuous modulation of the sent out light and you resolve the phase shift when it comes back. So these are physical technology tricks that are used to get a 2D sensor, imaging sensor for time of flight. But of course, still the pixel area is very important for the resolution in 3D. That means concurrently, it's not possible to build very high resolution 2D time of flight images or imaging sensors. In this case, the Kinect 2 marks the introduction of a VGA resolution in that field. So this is relatively low when you compare to concurrent 2D cameras. I said before that the time of flight technology does in principle not depend on the distance, except for the contrast that you get back. However, resolving this light travel time is also quite different, and that leads to those systems having typically accuracies in the centimeter range only. So there are limitations to get better with time of flight technology. So this puts them rather at the low end of the set resolution in these technologies. This slide shall give you an overview on the strengths and weaknesses of the different technologies that we have discussed as a reference. I will now present which technologies fit best to which kind of application scenarios. Now, after looking at this overview, let's look at a few application cases for the end. And we've mentioned often dynamic scenes. If you have controlled movement over the full object, then laser line triangulation lends itself to it naturally. You can scan a defined area very rapidly. So a typical application would be inspection here, detailed inspection of a rotating piece where you have the movement controlled. What about uncontrolled movement? Here I want to show you a particularly non-industrial application usually, but of course it can be the same in industrial settings. If you think about autonomous vehicles, these are not only driving assistance features, but also vehicles for transportation in a production environment and so on. So here, concurrent debate is that actually for driving assistance, a scanning LiDAR setup plus some stereo vision is the system of choice in many technologies that are currently brought to the market. You can see here on the lower right-hand side how the stereo camera in this car gives an almost filled representation of the, let's say, of the area in front of the car. What about taking snapshots? Again, not an industrial setup necessarily. And this technology has been brought into our mobile phones in the last years. What do we do here? Well, in general, first was the structured light approach in the infrared. So invisible light projected onto the face to create a 3D representation and use it to identify the onlooker. In this area, also time of flight imaging, so having 2D sensors to get time of flight data, is a viable alternative and is used in some of the devices. Let's move back to industrial setups. I've mentioned robot guidance initially, and this, of course, is one major area for industry. However, we'll have a separate vision channel feature on bin picking, so I will leave most of this out for this presentation in this overview. I just want to mention that bin picking and depalletizing, these are of course important applications for 3D cameras, but there are many more. I've shown here examples from logistics, looking into a trailer and detecting all the boxes correctly before unloading, and so on. As I said, please refer to our future feature on bin picking to get into the details of this application area. Let me instead cover a few other industrial setups like quality inspection, or in this case, shape validation. Here, our sensor cameras, so that is the active stereo approach, is used to basically trace the shape of an object. And in this setup on the left-hand side, 3D sensors are used to get a surround view of this part, and actually shape deviations are detected from comparing with its CAD model. On the right-hand side, also a CAD model is used on this seat cushion, and here the Ensenso data is directly fed into a robot guidance system that will mill basically the outlying features away to get the seat cushion in perfect shape. Here the accuracy is below the millimeter scale. Another important area for the 3D sensing is stability for different environments. So these are earlier setups that we have put our Ensenso cameras in. In this case, it's an outside setup to trace along the trunks, the tree trunk, and get their structure, their volume out of it. In this case, the camera need to work in harsh and cold environments, of course, because the tree trunks are sought also in Siberia. And on the right-hand side, it's the opposite. It's a very hot area, or at least an area or a room with a lot of temperature change in it, looking at fresh die-cast motor blocks. In this case, it's to detect the outliers, the remnants of the casting process, to cut them away correctly. You can find more information on the broad areas where our Ensenso cameras, the active stereo principle, lends itself to in our IDS case studies. Finally, let me give you an impression of what coverage is possible by the active stereo setup. In this case, I want to point out that these setups are very robust and very flexible for multiple purposes. We can cover dynamics and statics. We can cover small to large coverage areas. And as a final point, you can see on the lower right-hand side the kind of coverage that has been achieved using one of the larger Ensenso setups. So with this, I want to conclude my overview on 3D in machine vision. And I want to point out that we'll have a next iteration that goes over our Ensenso product line in the future in the Vision channel. So thank you for your attention.